Hello, everyone, and welcome to the Domino Data Lab Machine Learning at Scale with Amazon's X1 Instance webinar. I'm Eduardo Ariño de la Rubia, the Chief Data Scientist at Domino Data Lab. So this is sort of the contents of the webinar, what we're going to cover today. I'm going to do a short introduction just of who I am and why it is that I'm doing this presentation. That'll be in the motivation section. Then we'll talk about some benchmarks, and I'll give some attribution to where it is that I've gotten these benchmarks from, because a lot of them are not original work on my part. And then I'm actually going to switch over to the Domino Data Lab platform, and we will be doing a bit of a live demo where I'll actually be playing with these X1 instances. And yeah, I hope like I said, I hope you learned something. So just a quick introduction. I think it's important. So this is me. I'm the bearded guy right here. I've been a data scientist for quite a while. On the left, you see a Sinclair ZX Spectrum. That was my first computer in the early 80s. And on the right, you see my 3 dogs. A little bit of a timeline of how I came to be the chief data scientist at Domino. And why this X1 instance was really so exciting for me. I came through data science for a love of supercomputing. In 1997, I got my first account on a supercomputer, although today would hardly be recognized as one. It was a MassPar MP1 and a MassPar MP2. These were amazing machines with 2048 processors. However, they were 8-bit processors, so I'm pretty sure that like the new iWatch has more processing power than these. This processing power unlocked the ability to do lots of soft computing, as we called it back then, which is really what ML and AI has become. Genetic algorithms. I hired my first ML engineer in the 90s, and since then, I've been really pushing the limits of what you can do with computing, and with everything from traditional supercomputer architectures, which I had the privilege of working on, to what really ended up becoming the way that supercomputing was done, was clusters. And it's kind of interesting that, and we'll cover this a little bit in this webinar and in an upcoming webinar, how everything has come full circle, and you now are back to having these massive machines. So I was an advisor to Domino starting about 3 years ago, and I've now been at Domino as a full-time employee for about a year as the chief data scientist. So just wanted to show a little bit about what Domino is. So Domino is a platform for data scientists, and what it allows you to do is it allows you to run code. And that's really been the primary sort of design philosophy behind Domino. You can take your R code, Python code, Julia code, and we abstract away the actual compute environment, which is really 2 things. It's the hardware that runs it. In this case, we're going to be using the X1 hardware, as well as the packages that are required to get it to run, as well as the configuration, all of the dependencies and all of that. And we make it really easy for data scientists to sort of spin up and spin down these elastic computing resources to do experimentation. So you'll get to see more of that, more of the Domino platform as we go on. So let's get to the motivation. So what is the purpose of this webinar? And I kind of like to talk about, this is a famous slide by Andrew Ng. He's the chief scientist at Baidu, and he talks about how data and machine learning, as you're getting more and more data, the performance of these machine learning algorithms is increasing. He does show that, most machine learning algorithms are topping out in performance, and here performance he means accuracy, and some new AI methods such as deep learning keep increasing in performance as the amount of data increases. What isn't shown in this slide is that as the amount of data increases, the amount of computing resources required in order to process this data, to train models, to operate on these models also increases. You need faster and faster hardware. The way the world of computing has sort of matured at this point is really there's 2 primary branches of computing hardware. You're either going to be using CPUs or GPUs. For this slide, Andrew is primarily talking about GPUs, but I think that there's a lot of energy that can be wrung out still out of the CPU-based models, and we'll talk about them here. One thing that I did want to point out, and this is a tweet from Dr. Szilard Pawka, I'll be talking about him in a minute as well, is that there's this hype about the hugeness of data sets and how people are operating on larger and larger data sets. But the fact of the matter is that still most of the data sets that people are analyzing, and we're not talking about the raw data, right? We're not talking about the logs on disk. We're talking about the actual data sets that people are manipulating and feature engineering on and using to train models. have grown, but they've not really grown at the rate at which hardware and algorithms have grown. So this has allowed, there's this gap now between the velocity and speed of computing resources and the amount of RAM and the actual data sets that people are manipulating. So it's something to keep in mind. So let's talk about the X1 instances. So Amazon released the X1 instances a few months ago, I believe, at this point, and they're huge. What do I mean by huge? If you remember on my first slide about me, I showed you the Sinclair ZX Spectrum. It was a 16-bit computer with like 18 kilobytes of RAM. X1 instances have 128 cores. Now, these are not real cores in the sense that there's not 128 actual processors. They have 4 CPU sockets. Each one of those CPU sockets has 16 cores on them. And each one of these cores is hyper-threaded, which means that each one can execute 2 separate threads of operation at the same time. So they're huge on that vector. They've got massive amounts of processing resources. But they're huge on a second vector as well. X1 instances have access to 2 terabytes of RAM. It's really hard to convey how big 2 terabytes of RAM is. It's one of those things that the average, a couple of years ago, somebody did a survey of the average size of the average Hadoop job, and it was something like it was operating on under 50 gigabytes of data. So you're talking about the X1 instances have the ability to fit in RAM something like 20 to 50 of the average size Hadoop jobs just in a single in-machine instance. This is a massive amount of compute power that is available now just basically by clicking a button in Domino, which I'll show you in a minute. The thing to realize is that there's an architectural issue at play. These boxes, the way that CPUs and RAM intercommunicate is that DIMMs, the actual chips that RAM sit on, are basically assigned to individual CPUs. So for a lot of workloads, this causes a great deal of contention between the different CPUs. So if the algorithms in the libraries are not aware that they're being used on a box with this many cores, with this much RAM, with these many DIMMs associated to individual cores, it actually turns out, as we'll see in a minute, that it has some very, very serious impact on performance. So what is the motivation? I think it's important to go over it. The motivation is that datasets are increasing, though probably not at the rate that we would believe from the hype, and compute power is increasing considerably. On the cloud right now, at the push of a button, again, 128 cores, 2 terabytes of RAM is immediately available to you. So let's get to some meat and potatoes. Let's talk about some benchmarks. So we've actually measured some stuff, which is always nice. I want to do some very serious attribution. I have, a great deal of appreciation. A lot of this is the work of Dr. Szilard Pawka. He's a data scientist and professor of machine learning at CEU. You should absolutely follow him at github.com/Szilard. He's a close friend of mine, and really his work is beyond reproach. All of these benchmarks are basically available at these 2 URLs, and you should feel free to copy the code down, put it in your Domino account, and run it on the X1 instances if you want to tweak some hyperparameters or change some approaches and submit patches. I'm sure he'd be happy for that. So let's talk about machine learning at scale. When will computation at scale help you? So, there's 2 types of scale that I wanted to talk about because sometimes it gets a little confused. You've got some massive data set that you want to learn from, and that's one type of scale. The other type of scale is you need results very quickly. So large compute systems will not really help you you need results very quickly, it turns out. It turns out that there's this sort of diminishing returns that happens, both at the training, and this is due to the architecture that we were discussing earlier where the different cores are assigned to different DIMMs. There's also the fact that these models will actually just take longer to execute. And having a very, very large computer with lots of cores, the actual scoring of models is very, very seldom parallelized. So you can leverage the computational scale to get, point number 1, this massive data sets you want to learn from. You can train one very, very large model, and you can do that and spread the single model training across all of the computing resources on the X1 instance. Or you can train many, many models. You can do so via grid search, or you can do so just to hyperparameter tune to find the right exact configuration that gets the most out of your data. So let's actually stop for a second. So what is the actual expected use that Amazon had for these? When Amazon released the X1 instances, there was a lot of fanfare about SAP HANA. And SAP HANA is an in-memory column-oriented relational database. And I think that this is where the X1 instances really shine. As we know in the data science process, there's lots of different steps, right? You have to get data, then you have to do exploratory analysis and visualization. And only once you've really gotten some level of confidence about this exploratory analysis and visualization does it make sense to go into the model building phase. As we'll see, the X1 instances, they help model building, but it's asymptotic. But what they really enable is this ability to load these massive data sets into RAM and to interactively explore them. Whereas previously you would have had to go back to a database and pay a performance penalty. Every time you go back to a database, you're going back to disk, you're going across the network. There's only so many queries you can ask in a single day because just of there's only so much time that you have, and there's all this latency that is added. That's completely removed when you use an X1 instance. And I'm actually going to switch over real quick to Google Chrome. I've got this session right here. I jumped real quickly. So this is Domino. I've got a project right here, an airline model project. I've already got a notebook session open with an X1 instance. I open this session and it opens this up. I created a small demo script. So I'm going to go ahead and execute it. As you'll notice, one of the nice things that Domino allows you to do is it allows you to set a hardware tier. So this is just running on an X1 really easily. Whenever I execute this run, it moves all my code and all my data over. So I'm going to go ahead and do some, just load dplyr, load readr, and I'm going to load some, I call it big data. It's not huge data, right? But we're talking about 10 million rows. 10 million rows is quite a bit of data to be interactively exploring, but you could do 10 million rows on a much smaller box. One of the things that I'm going to do is I'm actually going to go ahead and I'm going to concatenate big data to itself 10 times, and we're going to get some bigger data. So this will take a second. While this is happening, I'm going to jump back over to the keynote. So just to close this up, the expected use is this interactive exploration, the ability to, in a facile way, do summary statistics on data sets, test hypotheses, and this is something that it does really, really well. So let's go back here. Okay, it's still processing. We'll give it a second. One of the nice things that Domino also lets you do is we can go to the runs area, and I can get details about this experiment in real time, and I can see the resource usage. So you can see it was idle for quite a bit. Here's where I kicked it off. So we're only using, one 50% CPU, which is, considering this as 128 CPUs, it's using half, but we're loading up the memory, right? We're up to 4.4 gigs of RAM that is being loaded. Okay, while this is happening, I'm actually going to skip ahead. One thing to note is that linear models don't actually need scale. What I mean by that is that even for traditional small and medium data tools like R and Python, you can train linear models on 10 million rows and 100 million rows, especially if you leverage stuff like Vopal Wabbit, basically on a single core, and you can get really fantastic performance on training. There's a lot of reasons for this. There's been lots of advancements in the code that actually allows you to train these linear models. You're not going to get a lot of value out of training linear models on massive multi-core boxes. There is a problem though, and I am talking here about dense data, non-sparse data, is that there's only so much value that linear models can get out of more data. As you see here, when we went from 10,000 rows to 100,000 rows, there was a huge jump in the AUC, but really after that, there's only so much that the linear model can learn further about this particular data set. And that's one of those things. If you're finding yourself wanting to train linear models, then you're probably not going to need the X1. The X1 isn't going to be something that really provides a lot of value. Okay, so here we are. So we now have bigger data. Bigger data is, let's see, what is this? This is 100 million rows. Is that right? Am I counting the zeros right? So that's a pretty big data set, right? So we can just look at this data set interactively. So for example, we've got this distance variable. Let's say that I want to do a summary on bigger data distance. This is happening, again, on 100 million rows, and it's going to happen relatively quickly, right? That was pretty fast. I mean, what was that, maybe 2 or 3 seconds at most? And from that, it was able to find, these summary statistics, the first quartile, third quartile, median, mean, max values. It's important to note that, again, I didn't have to go back to the database. This is just loaded in RAM, and it's 100 million rows. Let's look at how much RAM we're totally using at this point, and we're still, this is where it gets a little crazy, we're still only using 14 gigabytes of data. We're now using, I'm not going to be able to do the math in my head, but this is a very small single-digit percentage of the total memory available on the X1 instance. What is true, however, is that, and this is going to be sort of a theme for the rest of this talk, is that libraries, and a lot of the libraries that we use, be this in R or this is in Python, are really not designed to take advantage of these multi-core world and this massive RAM. So even stuff like, let's say we wanted to do a histogram of the same variable, the bigger data distance. Again, so if you think about it, it's kind of a crazy thing. We're doing a histogram on 100 million records, and that was pretty fast, actually, right? This is something that if you were doing this in a traditional setup, you'd have to go to a database, you would have had to write the query, you would have had to get it back, then you would have had to go ahead and do the ggplot. It would have been much, much slower. This is pretty powerful as far as I'm concerned. So we can do the same thing for dep time. When throughout the day are people actually leaving? This is so this is, by the way, this is the canonical airline data set. If you go to, actually, let me click over while that's happening, to Szilard, github.com/Szilard/benchml. He has a great many sample scripts on how it is to actually calculate how it is that he benchmarked machine learning models. And I would definitely suggest going ahead and studying this and using this as a foundation for you to benchmark your own stuff. But again, it was the same thing. We were able to very, very quickly do visualization on 100 million rows. This is something that maybe I'm a little, old and jaded, but this blows my mind that in just a couple of seconds we're able to visualize these massive data sets. So this is where, again, the X1 instance really shines. It's the ability to interactively load a massive data set and interactively play with it, do summary statistics, and do sort of this exploratory analysis. So let's go back real quick. So I just said that linear models don't need scale. Well, so what does that really mean? That means that nonlinear models really do need scale. It turns out that this is, and if you look actually at a lot of the libraries out there, particularly like XGBoost and H2O, they take advantage of multi-core up to a point, and they need to. These models are considerably more complex than logistic regression or any kind of linear model, and like it says in the benchmark, some traditional tools using single-core approaches just simply can't finish. They simply crash. R, for example, you can see R was unable to finish training this. I believe this was a random forest for more than 100,000 rows. It just crashed. And one thing that's important is, much like you saw how the performance, right, the AUC was very asymptotic here for the linear models. For the nonlinear models, you don't see the same behavior. So they're actually able to take advantage of this extra data. This is important. The message I want to convey here is that if you're training nonlinear data, if you believe there's nonlinearity in your data and you want to take advantage of it using a nonlinear model, then this is when you're going to want to reach for a large machine that is multi-core and libraries that really, really take advantage of it. So that sounds great, but so what's the bad news? So I want to start with a disclaimer. These benchmarks I'm showing you are on the current version of the libraries when I was able to run these benchmarks, or when I was able to get them from Szilard's benchmark repository. These libraries are under constant development, and they have truly brilliant teams and people working on them. So what I'm telling you today about the performance of XGBoost or H2O is under no circumstances guaranteed to be, their asymptotic best. They're going to make it better. These algorithms are going to, these libraries are going to take further and further advantage of this large hardware. This is just a snapshot of today, how they perform. And so just keep that in mind, is that this is just a snapshot of today and not a snapshot of how it'll be forever. So just to start off with some bad news. So XGBoost happens to be one of my favorite libraries, and XGBoost does not perform well and on these larger machines. One of the things that you'll notice is this sort of U shape to the actual to the performance curve, right? So you've got runtime on the y-axis and the cores on the x-axis. And what you find, and what Dr. Pafka found when he actually wrote this, is that on an X1 or an R3 that only has 32 cores, they're basically getting the same exact performance. And as a matter of fact, it may be a slight bit faster on one or the other, but it's statistically insignificant. But what happens is that once you get over a certain number of cores, the contention for memory, the contention for data that is on individual DIMMs begins to overtake any performance gains to be gotten by parallelism. If I remember my parallel processing class, this is kind of like one of the warnings of Amdahl's law, is that superlinear speedups or linear speedups won't go on forever. There's no free lunch here. So this is an interesting thing to know about XGBoost, is that XGBoost is not going to benefit from an X1 on a great many data sets. I would encourage you to benchmark this on your own, but it looks like there's really diminishing returns after about 32 cores or so. H2O does not have the same problem. So H2O does not have that U shape that you saw previously. So it does not give you a penalty, whereas actually parallelizing XGBoost across many, many cores on the X1 did have a penalty. H2O does not seem to have the same penalty. However, there are some pretty stunning, diminishing returns, which I think is to be, is something that intuitively, now that we've discussed how there's these 4 sockets and they're contending for RAM on all these DIMMs, you can actually imagine how that's true. Eventually the overhead of getting the data from the DIMMs is going to eat up the performance, the potential performance gains. Again, so this is not guaranteed to be the way it is forever. I believe that they're, my understanding is that they're probably working on improving, the performance of these libraries on non-uniform memory architectures, but this is the state of the art as I see it today. I wanted to do a little bit of on deep learning as well. H2O has a really, really nice, dense deep learning library. So this is not for convolutional neural networks or for LSTM or any of those things. But if you've got a traditional dense neural network, H2O.deep learning is really pretty great. And what we've got here is we show kind of the same pattern, as the number of cores goes up, on the y-axis. The runtime, there's a clear advantage in runtime in going from 8 to 16 cores. There's a clear advantage in runtime, but less when going from 16 to 32 cores. But there was no measurable difference in runtime going from 64 to 128 cores. So this is one of those scenarios where the deep learning algorithm, it wasn't penalized by going to this many cores, but it didn't gain an advantage. One quick note: H2O's deep learning algorithm is interesting because it uses CPUs instead of GPUs. So if you're stuck, without being able to have access to GPUs, although if you have access to Domino, you always have access to GPUs. You can still train some deep learning models, and we can actually show this here in a second in the live demo portion. And last, I believe this is last, I wanted to show that Python also has actually a pretty reasonable performance curve. So this is actually training a Python random forest, and Python scikit-learn has this, really nice n jobs parameter. And what we see is a very, very similar curve, right, between these two. There is a massive performance gain from 8 to 16 cores, from 32 cores to 64 cores. There's still some from 64 cores to 128 cores. There's still some performance gain, but you can see that there's some, pretty real diminishing returns. So I'm going to stop here with the benchmarks. I guess the summary of the benchmarks is that some libraries actually penalize you for increasing parallelization. Some libraries do not penalize you for parallelization, but there is a pretty severe diminishing returns after some point, and that at the highest level, most libraries haven't yet caught up to this amount of massive parallelism. They probably will. It'll probably be relatively soon. But today, it's not. It's not a free lunch. You're not going to be able to just take the same approach that you've been using all along, put it on an X1 instance, and get some massive performance gains. So let's go to a bit of a live demo. So here I have. I have Domino spun up. I've got, again, I'm running on an X1 tier. I can just go ahead and load this. And so what I have here is I have a script. Let's see which one. I'll run this deep learning one first. So for example, this is just a deep learning script using H2O.deep learning. I'm going to load a 10 million row data set, and I'm going to go ahead and train it. And what I wanted to show is, let's go ahead and run this inside of Domino. Let me try that again. Live demos are always the best. Let's see. Excellent. So now it's uploading the data, I believe. Let's see if it actually uploads it. Okay. So it looks like while I was idle, something timed out. Give me just a second. And what I'm going to do is I'm going to stop this. One of the nice things about Domino is that I can actually just stop these and restart them pretty easily. let me go ahead and restart the RStudio instance. So while this is spinning up, I'll actually tell you a little bit about Domino. Each time you run one of these, it's saved in our reproducibility engine. So all of the changes that you've made between all of them is automatically saved in our revision file store. So I don't have to worry about having lost some information or lost some data. Domino makes sure that I had that all available for me. So here we are. In that amount of time, I was able to spin up a brand new X1 instance. Domino went ahead and copied all my files over. So I'm going to go ahead and re-execute this. Let me install the latest, greatest H2O as well, and we'll be able to see this just fire off. Let's see, it's installing. While that's happening, I'm going to switch over to this RStudio session. So this is the other RStudio session that I had right here, and what I wanted to show is using Caret, which is an R package. I'm going to go ahead and also load, load Caret, load the doMC, which is a parallelism package inside of R, load reader, and we're going to go ahead and train a GLM using all 128 cores. Let's see if this is kicked off in the meantime. Excellent. So this is going. One of the nice things that Domino has recently released, and I wrote a blog post about this, is the ability to secure shell to your instances. So I can go ahead and copy this, go over to my iTerm, and secure shell over to the box. And I was able to set up my secure shell keys earlier, but here we are. We're now actually running on these instances. I'll go ahead and make this window a little bit bigger for you so you can see it. So what is it that I can do? I can look at HTOP, and this is pretty cool. I don't know if you've ever looked at HTOP with this many cores, but we can see that H2O's deep learning really is leveraging all of the cores on the box, which is pretty amazing. Let me make the window even a bit bigger than this. Hopefully, it's coming across on the webinar how completely crazy this is. We're still only using a small fraction of the available RAM, but all of the cores are being kept busy. Unfortunately, like we said earlier, it's not actually giving us the speed up that we would hope for, and that's because a lot of the time is being spent copying RAM back and forth between the different processor sockets. So this is pretty cool. I think I can do that. No, I don't have IOStat installed. So one of the things that I can do is let me go ahead and stop this while it's training. We can do the same thing with the Python script that I have. I believe I've got it in here. So we can look at the random forest Python script that I have, right? And here we have, and this is all again through our SSH functionality. And let me go ahead and execute this. So Python rf.py, and we'll say to use 64 cores. And I can go ahead and put this in the background, and if I look at HTOP again, well, it looks like, that's right, it looks like there's a small error on this one. So I'll actually jump out of that for a second. So let me go ahead and load the GBM as well. Oh, so grid searching is another thing that is useful to do inside of multi-core environments. So what this allows you to do is it allows you to do hyperparameter search. If you remember, I said you could build one massive model, or you could build lots and lots of models in parallel. However, this kind of falls to the same problem that everything else falls, is that you're looking for the total number of CPUs is going to sort of stomp on each other because they're always trying to load RAM from each other, load data from each other's DIMMs. So I'm going to go ahead and actually load this, run this. This is using H2O's new, well, actually, I guess it's not new at this point, random search strategy. It's really quite powerful. There's some really great papers about how random search provides really great hyperparameter searching. So let's go ahead and execute this. I don't need to install H2O since I installed it already. And so here we go, it's loading the data set, it's executing. So now what is it doing? Given all of these possible hyperparameters, it's constructing a hyperparameter space. We create a list, we create this search strategy, we say spend at most 120 seconds, test 1,000 different models. This is when you want to stop. So it does early stopping, so it's not going to waste your time and it's not going to waste CPU resources, which is nice because the cloud resources are paid for by the minute on Domino, which is the difference between Domino and traditional AWS is that on AWS you pay by the hour, on Domino you only pay by the minute. So here we are, right? The hyperparameters are being searched, and if I go back to here, I can look. We can see that sure enough, it's using lots and lots of the CPUs. You'll notice that they're not being utilized 100%, and that's probably due to IO weight and the memory copying that we discussed earlier. So this was really what I had available for the live demo portion. What is the moral of the story, I guess, at the highest level is we now have available these massive X1 instances. They're available, to be very, very clear, in Domino. All that you have to do is go to the hardware to your section, and you can just literally go to the dropdown, click like this, and all of your compute environments and everything and all your projects will be installed on them automatically. You don't have to provision boxes and burn AMIs and do anything like that. And these massive boxes are available to you basically at the click of at a mouse click. If you're going to use them for interactive data exploration, for data sets that just would not fit in RAM anywhere else, they really work quite fantastically. And even using just pandas or R data frames, and particularly the R data table package, they allow you for really fast searching, so really fast manipulation. However, the title of this webinar was Machine Learning at Scale, and I think one of the most important things to take away from this is that the libraries are not quite there just yet. There are performance gains to be had. H2O is probably ahead of the pack at this one, I'd say, compared to some of the other libraries, but they're not quite there yet. You're not going to get the advantage that you did, when you went from 2 cores to 4 cores or from 4 cores to 32 cores. It's not going to be the same kind of sort of free advantage that we've grown to know and love with multi-threading, and that's unlikely to go away immediately just because of architectural constraints. But with further research by these, by these organizations building these libraries into how to deal with non-uniform memory architectures, we will probably get a great deal of value over time. So that's sort of the conclusion of the live demo and the sort of scripted part of this webinar. I think if there's any questions, we're going to switch over to the questions. So I'm going to put myself on mute for a second, and we'll see what the questions are. I'll be right back. So the first question is, I read your previous blog post, and one of the challenges you mentioned was the difficulty of loading up datasets from CSV. Was this a weakness in the CSV parsing libraries, similar to the other library issues you highlighted, or Amazon hardware issues? Any approaches that you'd recommend? Yeah, so that's one of the kind of, we actually had a really fun argument here at Domino Data Lab about this. There was folks who were actually completely incredulous that it could possibly take so long to load data off disk. Again, this is just, human intuition fails in high dimensions and in large numbers. The weakness was absolutely parsing CSVs is, it's a non-trivial problem. So what bits of advice would I give? What approaches would I recommend? Try not to load data off disk. If you can load it once and then keep that memory image around, then obviously that's good. There are some really, big differences in the performance of CSV reading libraries. So, for example, if you take traditional R read.csv, that's much slower than Datatable's fread. Datatable's fread is much faster, and I believe if you look on our blog, I wrote a blog post about this, that it's much faster. Also, there's some formats that have come out recently. Hadley Wickham and Wes McKinney have worked together for the Feather format, and that promises to be pretty performant, although it's not super performant. If you're using Python, there's a library out there, however, that is really cutting edge. It's the Paratext Library. And it's actually a multi-core aware CSV parser, which if you would have asked me 10 years ago whether those words would even make sense put together, I would have told you were a little crazy. But no, it turns out it works. It works real well, and it'll cut down the load time to some very small fraction depending on the number of cores. Now, it won't score infinite. It won't use multi-core infinitely, and there's a lot of reasons for that, right? Like it has to. I haven't studied it deeply, but I don't think it parallelizes past the number of columns. Although I'm not sure what the true limitations are. The answer is that yeah, it's tough, and loading it naively, loading a terabyte of data is going to take 4 hours, and that's an awful long time to get a terabyte of data into RAM. So play around with some of the nicer libraries like the data table library, like the Paratext library. Leverage them, load data as little as possible as you can. Load the smallest amount of data that you need, which I know is ironic considering we're talking about having so much RAM. Yeah, that's what I would suggest. It is not, it's not an issue of Amazon's hardware. It's really, you can test this on your fancy new MacBook Pro. Like reading CSVs off disk, even super fast SSDs is still kind of a slow thing. All right, let me see if there's any more questions. I'll put on mute for a second. So the second question, these are really great questions. The in-memory data exploration is exciting. I agree. Did the database library scale to handle the large data sets? So that's a great question. The answer is sorta, right? As you may have seen, I was actually really shocked that R's base plotting like was able to handle like plotting a histogram on 100 million rows, like with a plum. It did like a pretty great job. Now, histogram's kind of cheating, right? Because we're binning and summarizing before we're visualizing. But at this scale, right, like you've only got so many pixels on your screen. So any approaches that visualize this much data are going to be doing some sort of binning, either explicitly with a binning phase before visualization, or implicitly because literally they're just going to be drawing on the same pixel over and over again. There are some libraries that are really like hang their hat on being able to scale to very large data sets. Python's bokeh library, for example, does a fantastic job of this. This may be just this may be a problem that I had just because I've got not the world's fastest laptop, but it actually crashed my web browser. I think it was just trying to draw too many points, too many DOM objects, but it also may have been that I wasn't using the latest version of the bokeh library. It's one of those questions. What is it you're trying to visualize, right? And does it make sense to visualize from the raw data set, or does it make sense to use a dplyr or pandas command to do some binning or some tiling to get a heat map out or something like that? And picking the right visualization. There's a question: what are you hoping to get out of a point plot with 100 million points on it when you just don't have that many pixels to actually discern? It is exciting. I think there's going to be some great advances. I had the good fortune of speaking with Hadley Wickham, I think a year or two ago, and this is stuff that he's thinking about. This is stuff that folks in the Python data visualization community are thinking about, the JavaScript data visualization community are thinking about. If you're talking about visualizing this massive data, you're on the bleeding edge. You're absolutely on the bleeding edge. Expect to feel some level of pain. To bring it all back around, the in-memory data exploration is exciting. Right now, what really flies on it, what you can crush, is doing summary statistics and basic visualizations. Things that would have been still really painful to do in the database world, you can still do today using these X1 instances. All right, so I see there's a third question. With diminishing returns after 32 cores, is this an indication that developers haven't optimized, or are there inherent issues with the multi-core architecture? So this was the question that destroyed the world of supercomputing in the 80s and led to the creation of Amdahl's law. It was the belief that this sort of thing couldn't be done. The answer is yes to both. There is absolutely components that developers haven't optimized. A lot of this, there's fantastically good reason for it. If 95% of your users are going to be using 16 cores, then kind of as a developer, it's a little wasteful to spend a lot of your time, your waking moments, working on optimizing for this like bizarre edge case of 128 cores. It's something, like I said, this is going to become the new normal over time. Those of you in the webinar, a year or two or three from now, when everybody's talking about these large machines, you'll be like, oh yeah, no, I've had experience on this for a couple of years, but the libraries are going to catch up. There's things that they can do about being smarter about cores. Some of the work that Dr. Pafka has done has shown that there's massive performance improvements to be had by just using CPU pinning. So making sure to pin individual process to individual cores so that that core is always accessing the same RAM, so that you don't have this DIMM contention. I think we were discussing earlier last week, and he was saying that he believed that there could be up to a 40x speed up using really, really smart CPU pinning. So there's absolutely gains to be had, and there's massive gains to be had. And I'm sure they'll come soon. Again, the people working on these libraries are some of the best and brightest people out there. That being said, all that being said, there's absolutely some limitations, right? As long as DIMMs are paired to sockets, and as long as accessing memory that is not in your direct, in your direct fastest path requires jumping across, the speed of light exists. Right, the speed of light is a thing we're going to deal with, and there's only so many electrons you can shove on a wire that when multiple cores are contending for it. I don't think that this is some sort of death knell to multi-core architectures. This is more hey, there's more work to be done, and there's a lot of opportunity for folks to really like do some groundbreaking stuff. Fourth question. All right, what are your thoughts on claims by commercial R vendors around the performance they achieve using large on-disk data sets? So it's a bit of a tough question. I don't know which commercial R vendors you're talking about and which claims. Best I can do is ask those vendors what they're thinking. So that being said, I'll take a slightly higher step up on that and say that there's a lot that you can do with large on-disk data sets. The way that disks have gotten really, really fast. We're no longer in the world of like weird old spinny disks that take forever and make chunking noises. Like, the performance latency and the difference between RAM and the most cutting-edge solid-state drives and has really gone down quite a bit. I'm a big fan of columnar data stores. And whether they be in memory columnar data stores like SAP HANA or on disk columnar data stores, and there's open source ones like MonADB, MonADB Lite, and commercial ones out there like Vertica. Turi. I don't know if S-frames are still available. Turi did some fantastic work with S-frames. Yeah, the fact of the matter is that you can get some incredible performance out of on-disk data stores that use a columnar layout of bytes on disk. They use fantastic compression frameworks so that each fetch from the block device is actually fetching a considerable amount of data. They understand cache awareness so that as things are coming from disk to RAM to cache, you're never actually thrashing your pipeline. There are some truly fantastic advances to be had there. It'll never ever be as fast as RAM. Right? Like that's just because that's how that works, because RAM is faster. But the fact of the matter is that there is a lot of advancements to be gained. Right? The question you have to ask yourself is, would you rather pay the penalty of loading and interacting from data on disk, even through the fastest columnar data store, or do you want to pay the penalty once of loading the data into RAM and then having facile access through the direct direct APIs that you want? So let's see. I have hopefully that answered that question. Next question. Question, you made a brief reference to Domino's reproducibility engine. What are the use cases and what problems does it solve? Okay, so that's a pretty great question. If you've ever scaled a quantitative analysis team or a data science team, one of the most important things that allows you to scale these teams is the ability to create a shared context between people that work together. And that's really, really hard to do. And it's important to be able to create this shared context and to be able to create sort of this ability to understand what everybody's working on. I'm going to actually just switch over to the browser real quick. So for example, let me see if I can just pull up my evaluate model project. So here I have an evaluate model project. So what is Domino's reproducibility engine? Every time you execute something in Domino, goes out, it takes a current snapshot of your project at a moment in time, right? So I'll go to the files tab for a second. These are all the files. These are all the experiments that I've run. Domino intelligently stores the deltas so it doesn't waste a bunch of disk. It finds some hardware in your Domino cluster, that can be on premises or it can be in person. Or it can be on premise. It can be on premises or in the cloud. It spins up a Docker container and installs all of your dependencies on it, moves your code, and executes it. So what that means is that, so for example, here I was here. We'll look at this one. I was evaluating a model that was naive Bayes. That was looking at the iris data sets, a really huge data here, to classify the species column. So I can actually look now and I can see that this is the exact run that I did on November 4th at 11:17 a.m. These are the exact code. I can go to the details tab. I can look at the exact input files that happened. So what use case does it solve? So let's say that I was working on this project with a coworker. We can have a discussion specifically about this particular experiment. I can go to the results. So let me go to the results real quick. And so we can have a discussion about, I don't know, so here's a confusion matrix of naive Bayes, and I can be like, so for example, I could be like, I don't know, Jennifer, did you notice how versicolor and virginica get confused. And Domino's reproducibility engine sort of serializes this comment to this particular artifact for this particular experiment. And that's really, really powerful for a number of reasons. I can now go to the discussions tab, and anybody who's new who comes into this project can see the conversations we've had. But the final thing that it allows me to do is it allows me to do really cool meta-analysis. So for example, I can click on this when we were training this naive Bayes model and this k-nearest neighbors model, and I can do side-by-side comparisons. So since it ran in the Domino reproducibility engine, it knows all of the artifacts it generated. And so from here, I can look at the diagnostic statistics. I can look at the difference in accuracy versus naive Bayes and k-nearest neighbors. I can look at the actual IntelliJ Blender R data files. I can look at the plots that it generated. And so, for example, I can overlay the confusion matrices over here, and I can look at, see the difference in the k-nearest neighbors to the naive Bayes. So that's what the reproducibility engine allows. It's anything that is executed in Domino, we capture the state when the run has started. We capture everything about the run while it's happening. We capture the outputs of the runs, and we serialize it in a system of record that allows you to basically to do meta-analysis, to discussion, and to create sort of a shared context. So looks like that was it. Looks like that was all of the questions that I had. So thank you very much for your time. It was really enjoyable. If you want to send me an email, I'm Eduardo at dominodatalab.com. I hope you learned something. Have a great day. Thank you very much.